Chapter 7 is up next. This broadcast will focus our intention on Chapter 7, and the main emphasis here is obviously circulation of the atmosphere. So, we're going to continue on with our material here and try to drive through some new content. We've got a fairly distinct level of information here. Nothing's overly complex when we look at it, and what we're looking at here overall is small and large scale circulation. Several different types of concepts: micro, mesoscale, and macro scale. Micro scale being something that's small, and that's what we see when we have different types of very, very local types of winds or very local types of events that tend to take place. So when we see those types of micro scale events, we're talking about maybe city level, maybe a couple city levels. Then mesoscale, we step out and we're talking about something that's more widespread. So this may affect a region. This may be something that the weather service or a local broadcasting station is really emphasizing a great deal of concentration on. Something that on the mesoscale could last a few hours, and it's definitely something that's going to impact you. So think microscale, maybe something impacting your house; mesoscale impacting your region, which could be including your school or a group of schools in a corporation and associated properties. And then macro scale gets much larger than that. Think planetary. So a few characteristics here. We're small, chaotic in the micro scale as I was. So small, chaotic wind scales at the micro level. They can last from seconds to minutes, very strong bursts, and they can do some significant damage. Sometimes it's not so much damage. Most of the damage here at the micro scale is done at the what would be considered an unimproved structure level. So think of a wood frame barn, particularly those that have a bit of an age on them. They can be simple gusts, downdrafts, small vortices, dust devils. We've seen these things before. Think about the simple example during typically a spring day where you see leaves or debris being curtailed up into a cyclonic or some type of a spin in the corner of a building, similar to that. So we don't have great expanses of agricultural properties as they do out west, but we still have an idea though. Let's step out to the mesoscale winds. Minutes to hours, these are things that do affect you, and typically these grab our attention. They're going to cause a much wider disruption to normalcy. So we're not talking about an immense entities here. So about 100 kilometers across is what we're dealing with. Some of these, like tornadoes and thunderstorms, have strong vertical components to those. So think back to our clouds when we're talking about those of vertically developing natures, cumulonimbus, those types of structures, or even the cumulus that are associated with thunderstorms and then potentially even tornadoes. They do have these updrafts that can be likened to that precipitative environment that is generating hail that we talked about in previous sessions. Macro scale, these are very large wind patterns. Think on a planetary level. So this can affect an entire hemisphere or even more, and that gives us the idea of those typically traditional views of planet Earth from afar. So if I were on a trip to the moon, about halfway between that, I might turn around and look back at Earth, and if we've got a lot of clouds suspended in the atmosphere, we would probably see those swirling. That's what we would describe a macro scale wind to be like, or a macro scale level. Synoptic scale is another word that we refer to macro scale with. So we're talking about 1,000 kilometers in diameter when we look at those. Smaller macro scale systems are called tropical storms and often referred to more commonly and most frequently as hurricanes. So things here we need to make sense of. This is one that sometimes gets confusing just because of all the names involved. So think macro scale. Macro scale is a planetary scale, and that's what we see with that typically hurricane-like entity from space whenever you have that definitive eye in the middle. Most of you understand what we're talking about when you have that clear eye. That is also, macro scale is also talking about a synoptic scale. A synoptic scale is a very large process, and what we're talking about as far as a value is 1,000 kilometers, and we have a more precise common definition of these that can be tropical storms and hurricanes, not extra tropical storms, but tropical storms and hurricanes. So a lot of linkage there, and work on connecting those together. That's about the only hurdle within this small group of introductory content. Here's a nice graphic to understand what's going on with these systems. So we've got this type of a suspension. What this image is trying to show is we've got a common processes like little edifications of the wind around the corners of your house. We talked about leaves before. You could have paper, you could have small debris. Probably in a stadium, you've seen this before, particularly in a football stadium, maybe under near the bleachers or in corners of trapped regions. And that would be something that is a micro environment. So all this is micro environment. We only have a very, very brief amount of time, very small. Then we get into this tornadic circulation, and this is where we get into a larger scale. And that's where we're focusing on these things that can last for a little bit longer. You know, they can last from hours to sometimes days, depending exactly what we're talking about. And that's definitely our connection to tornadoes. And then we get into a planetary scale, and here's our hurricane, our traditional look at that. And that's what we're talking about with a macro scale. So we have a micro scale, meso scale, and macro scale all put together there. Structure of wind patterns. Global winds compose motions on all scales. Hurricanes are large entities that move slowly across the ocean. They have the battery of winds that aren't overly aggressive. They're actually not quite as intense as a tornado, but they just don't stop. They just continue on, and they're slow moving, so they just keep berating the same area over and over again. The large cloud will contain many mesocyclone thunderstorms. And by a large cloud, what we're talking about is a hurricane. So that's going to contain many mesocyclone thunderstorms. And what we've seen in our region before is when a very strong hurricane happens to make a very particular track where it's going to trace into the interior Midwest and over Indiana, we can see a pretty aggressive outbreak of severe weather. And we've actually had tornado outbreaks that come from a south direction, and that's because of the breakup, almost shrapnel, if you will, from a hurricane. Not very common, but certainly potential. The thunderstorm consists of numerous micro scale bursts, and that's a major problem with aviation. We'll discuss that in class, but these micro bursts, we have a couple different types. We have the outflow and rotor, and those are problematic because they affect an airfield slightly in slightly different ways, and the aircraft is implicated differently. So it's required a bit of a retraining over a period of a decade or so, and or longer, and that's continues to be a challenge for our airfields. Land and sea breezes, we've mentioned these before. We're going to build on this in a little bit. Here's the challenge within this portion of the course. We need to understand a couple different things about this. For one, this is what we worked on earlier. We're going to use this 1000 millibar level. And what I'd like you to do is be able to dissect the atmosphere aloft versus at sea level. So when we see the high to low flow, we'll definitely see that follow our pressure tendencies there. And then when we get aloft, we're going to reverse that flow. So we do have our land and sea breezes. Land breezes are characteristic at night because the land loses its energy and it's going to get cool. That thin layer of radiation just isn't absorbed very well. Compared to the water, we get a greater level of penetration at depth with the water, and so it's able to hold on to that. Plus, we bring in our specific heat capacity there, and all those roll together into low pressure at night. When we reverse the time of day and we go to the daytime, then the water is being cooler than the land. That shallow profile of land heats up more quickly than the water. The water dissipates and spreads that energy into greater depth. Plus, it takes time, again, the specific heat function there, and we see a reverse of that. So do work on making sure you can make strong connections to the land and sea breezes and articulate between areas aloft, like you see here, versus area at sea level. Those are two things there that we need to work on. Mountain and valley breezes. These guys are different. We haven't talked about them before. Concepts exactly the same as before. We just apply a different thought in regards to geography. So here we are in the valley during the day, and we have cool air that's sinking. And as it subsidizes, it's going to create a more dense profile in the middle of this valley. That valley then is going to push less dense, more buoyant air up, creating a breeze from the valley up the slope of the mountain, meaning it's called a valley breeze. So let's reverse this and move forward in time and talk about what happens at night. At night, we're going to have more dense air from the top of the mountain sinking down first. Warm air is going to rise up, and then that's going to, because it's more, it's less dense, and as that happens, then we create a different type of a breeze, and that's a mountain breeze. And the reason why it's called a mountain breeze is because it originates at the top of a mountain. So points of interest here: mountain breeze occurs during the day, valley breeze, as I was. Mountain breeze occurs during the night. Mountain breezes occur during the night. Valley breezes occur during the day. Chinook. These types of winds, also referred to as foehn winds, these are winds that are often referred to as snow-eating winds. Native Americans and other societies refer to those because they've seen snowpack be eaten by these warming winds, and these are adiabatic processes. These are warm, dry winds that sometimes move down the slopes of mountains. So if you can remember back earlier in the course when we were talking about adiabatic process, and that's where we have that compressional force in the atmosphere, and that's driving temperatures up. We're not adding humidity, so that warm, dry air flows over snowpack and it makes snow disappear. So we have these names that have no English language connection because more ancient persons on the planet noticed those types of things. And typically they occupied areas slightly west of our current location in Indiana. These can bring on drastic changes in temperature, and believe it or not, they can be a little bit disruptive to society. There's been some psychological profiling of certain cities that have Chinooks, and there is a very strong correlation to delinquency in society and the appearance of a Chinook. So it appears to be almost an abrasion in society, if you will. There's an irritation level that seems to be somewhat intolerable to a densely populated city. And when we have Chinooks, then crime rates go up. Very odd association there. The winds will melt snow cover rapidly. Native American Chinook means snow eater. That's where it came from. Basically, they were watching snow melt, and it melted quickly, and that was surprising to them. Similar winds are called foehns in Europe. So we do have these areas in different parts of the world. We're going to refer to the concept of Chinook here because that's what we'll experience the most. We do have Chinook wind effect in Indiana. It's not very often. It's an odd warming wind, and it comes out of the west most of the time. Most of the time, generally, our warming winds will come out of the south or southwest. Every so often, it seems like once every early spring or late winter, we will have a little bit of snow on the ground, and we'll have a warming wind from due west. And a lot of times that's because of a change in elevation. We'll talk more about that later when we get into the part of the course that discusses dry line. It's a similar effect there, except we bring in humidity. Katabatic winds, fall winds. These are winds that are affecting different types of aspects within the atmosphere. Basically, when cold, dense air begins to move, we get these winds that are present. Sometimes they're referred to as mistral winds, and that's when we see this type of a flow from the French Alps to the Mediterranean. And what we get into is with these types of winds, we begin to get this migration of a cold, dense air mass, and it begins to move over sometimes mostly warmer air. So it can be associated with fog banks and things of humidity nature that's a bit uncommon or sudden. This is not an area that typically affects us. I can't remember too many of these types of mistral winds affecting our region in this country. Country breezes, definitely. We have these. These are mesoscale winds. We have these every so often, and they're caused by the uneven heating of the urban and country areas. This is where we bring in the heat island effect, and that's something that hopefully you've heard of before. The urban heat island refers to the building materials, dense populations, and typically pavement and concrete that is prevalent in cityscapes. And those retain energy. And so what we typically have is during the summer, a warmer cityscape, a warmer city atmosphere on the mesoscale level. And then we have a cooler country. And then what that creates there are breezes that affect certain regions. So the result in a flow from the country to urban areas. Why would that happen? Because we have a difference in pressure. We have a difference in heating capacities there because we have different materials that can hold on to things. And so we do see those types of things as well. Further on that point, we can actually have a much more detailed wind around larger buildings. And some of you have probably been in maybe a city like Chicago or even downtown Indianapolis, where maybe even at times downtown Louisville, where you have a large building, and it always seems to be a bit more windy than normal. So we can have a human aspect that does generate a different wind appearance on this planet whenever we start to build larger structure. On to global circulation. Here's where we get into convection cells. We have a couple large convective processes here. This is the Hadley model. We have one that we'll talk about in a little bit, dealing with the Farrell model. And this considers a single cell circulation model. It's incorrect. If you look at that diagram, you'll see hopefully why that is incorrect. Look carefully at the planet. This diagram is not showing that it is in motion. So this is a model that depicts a planet that is not moving. What this proposition is that the contrast in temperatures between the poles and the equator will create this huge convection cell. Think convective heat process like we talked about earlier. And then that's where we have the rise near the equator, less density. And then we have the flow toward the poles. This is similar to that same aspect we talked about with our country breezes. So the rising, the heat there is the urban heat island in the cityscape. That rising takes place, and then it's replaced by cooler air that is more dense from the countryside. So we have a country breeze. Three-cell model. This model takes consideration of the planet's motion. And this is where we get into Hadley cell and Farrell cell, and we start to develop a greater depiction of a more accurate wind flow on a permanent or semi-permanent status. So we still have a dimensional aspect where the air is leaving the planet, but we're also bringing into effect a little bit of the Coriolis. We're bringing into effect a little bit of these constant pressure tendencies, and it definitely connects to latitude. So I need you to remember three things here with latitude, because these are going to be important benchmarks. We've got our equator, 0 degrees. We've got 30 degrees. That's our subtropical high. We're going to refer to this as horse latitudes, and we'll talk about why in class. I want you to remember that 0 degrees, we have our equatorial low, and we're going to refer to that as a weird word that's called doldrums right there. And then we're going to get up here into our 60 degrees. And the thing that I'd like you to remember about 60 degrees is this is where our polar front is typically correlated to. So that's a pretty important front whenever we start to talk about winter precipitation, especially when we look at the year of 2014. The winter of 2014 was a very active polar front year. That polar front was unusually southerly in latitude, and that created a significant disturbance in our normal winter conditions. We had a lot more snow and many more cold days below freezing than normal during that season. All these models were proposed in the 1920s, and there is a very strong link to that development in wartime efforts. Historically, what we found is, specifically in meteorology, as well as other areas in science and society, we've had great advancement during times of war. And the reason being is because an advantage from one country is sought. So when we want to go back to these models, when we were seeking to improve our ability to become a commanded air force, or a commanded air presence, or a strong naval presence, a strong navy, or a strong sea presence, then we needed to know more about the winds, about the weather, because we could use that as a cloak or some type of a camouflage in a natural sense. And we still do the same thing. Those are things that we continually look for, is how can we use the weather to improve our situation when we're looking at an advantage globally. What we see because of this is warm air rises at the equator. That's connected to Hadley's work. The air flows poleward. It begins to cool and sink. Why is it cooling? Because it's farther away from the equator. Then it's going to sink at that 20 to 35 degree latitude. I want you to remember right in the middle of it, we're going to shoot for 30 degrees, and we're going to call that the horse latitudes, if you can remember that. Trade winds will meet at the equator, and that's a weak pressure gradient called the doldrums. Sailors didn't like that area. They got depressed. They got saddened because their winds weren't propagating them around the planet. Their sails were not full. They were at the mercy of the currents. So the doldrums is not a good area to sail. Your sails do not catch the wind there. There is wind. It's just vertical opposed to horizontal. The westerly circulation of the surface winds, prevailing westerlies between 30 and 60 degrees, called the Farrell cell. So if you can remember, the strong thing for us, because this is your band, this is where you live. You live in the Westerlies at the school's campus location, and that is the Ferrel cell. So Ferrel cell did work between 30 and 60 degrees, and that is prevailing westerlies. Hadley did work in the 20 to 35 degree range, and that's what we defined as the horse latitudes. So the one that made the most impact on your understanding of weather, because most of you have done very well talking about the wind bringing significant weather from the west, and the major reason why we can say that is because of a gentleman named Ferrel. Circulation at 60 to 90 degrees, that's a polar cell, and these are polar easterlies. So do you see the difference between this? We have the easterlies, we have the westerlies, and we have the easterlies. So this is a lot of content. It is a little bit of geography, and it's certainly a little bit of dynamics and pressure. However, there's a nice trend there that plays out. So these two slides that we've just gone over have a considerable amount of information. Idealized zone pressure belts. We need to get into these a little bit. The ITCZ, Intertropical Convergence Zone, is something that's pretty important, especially when we consider very pattern-based weather in certain areas. Subtropical highs are typically in an area around 20 to 35 degrees on either side of the equator, so it can be north or south hemisphere. Polar highs are where the polar easterlies originate, and that's what we see way up here at the top. So at this diagram, we have the polar highs, and that's what we're looking at, a high pressure. Now, can you remember, does high pressure at the surface, does high pressure have air that is subsidizing or rising? Is it sinking or is it rising? Should be able to recall that high pressure has air that is sinking toward the surface. So what we're having is a sliding down from the pole. And that's part of the reason why if you've ever seen anything about the locations around that part of the planet, it is very, very windy. So these Kadiabat winds that take place, that dense air, remember that weird term called mistral or Kadiabat? That's kind of what we're talking about there, that sinking, that density current that takes place. Most of you have probably felt that in some type of body of water when you've been swimming before. It's not exactly the same thing, but the process is similar. It's a good memory maker there, where you've been swimming and you felt a cool current or a cool pocket of air, and that's, or a cool pocket of water, and that's similar to that. It's not exactly the same thing, but it's similar. So these are all things we need to make sure we can connect to, which is a lot of material. None of it's too technical, but you do have a lot of connections here. So we've talked about the westerlies, we've talked about the trade winds, and we've talked about the ITCZ that's right here in the middle, right at the equator. Why is it called the convergence zone? Because the trades converge in that area. The westerlies is where you live, and that's where we talked about the work of the gentleman named Ferrel. And then we talked about that other region when we got into those, and that's where we dealt with the idea that dealt with Hadley at 20 to 35 degrees. So those are things where we need to connect to these slides. The other thing we need to generate an understanding of is these high pressures and low pressures. Some are almost fixed. They migrate a little bit. And why they migrate is because the equatorial low, or the ITCZ, these guys right here, these guys migrate a little bit. So what's that do to the planet? That sets things in motion. That creates a traditional seasonal shift of weather. And that's where we can get into things that's called like monsoon season or the dry season. And we have a monsoon season and we have a dry season at our location. It's just not nearly as pronounced. We have a much more spread out distribution of our rainfall. Semi-permanent pressure systems. When we look at the real world here, what we see is the ITCZ in January. Notice this is a January depiction. In January, the ITCZ is in this location. And notice how it does have a significant enhancement or significant difference whenever it moves over land. The reason why is, again, we're going with that specific heating. Land just cools down quicker than water, and we have a different aspect there. But do look at where these positions are located. We got the Siberian High. This high, Siberian High, we will look at. And the other one I want you to kind of concentrate on is the Azores High in that location. Those are two areas there that we'll bring into discussion that are fairly traditional. So here we are in July. Where did these go? So our July map is here. Same map, but the ITCZ has gone north. It is now north of the equator a little bit. And look at where these guys went to. So here we have the ITCZ way up into this part of India as it went over that. Now we've got an entirely different flow. So check your flow pattern here. We've got a flow pattern from the south and west over India there. Now let's go back a slide. Look at the flow pattern here. Entirely different than what we had. Remember the last slide, we had a southwest flow pattern. Now we are in a flow pattern from the north and east. So what we have is a very pronounced effect there. An entirely different type of weather pattern is present. So when we look at those types of things, it changes. It changes quite a bit. You can see the Bermuda High has changed in those areas of the Atlantic, and it alters that. So the key learning point here is when we look at the shift of the ITCZ near the equator there, we can have drastic changes in weather in certain parts of the planet. For your life, it's not a huge shift. Okay, we're fairly interior land, and it doesn't make a drastic difference, and it makes a nice tapered season for us. If we were more coastal located, we would have a significant change. So on to monsoons, we mentioned these before. The Asian monsoon we just looked at is a effect where we have the areas, China, Korea, Japan, other in Asia, which we mentioned on the last map, and that's driven by pressure differences, which we saw on the map. We do have an American monsoon, North America, and that affects Mexico. California gets hit by this. Rainy season, they've been in a drought a little bit. Hopefully going to come out of that soon, especially areas of Southern California. And those are regions that are also under monsoons. We just typically don't call them that, but most of you can probably remember and reflect on our spring seasons being much more rainy than our fall, winter, and summer seasons. So in essence, a monsoon is driven by extreme temperatures. Low pressure is what's at the heart of that. Monsoon is kind of related to a precipitation system. And what happens in the U.S. is low pressure over Arizona is developed, and it results in a circulation pattern that brings air from the Gulf of Mexico, moist air. And that's that maritime tropical that we will talk about in class. And that's where we see this geography again. We've kind of highlighted this before. What we have here in the lower corner is somewhat of a modified climograph. We'll work on those in class, but right now work on making a strong link to monsoons. We will focus on India the most because this is one of the more pronounced areas on the planet. However, do make sure that you can connect to the monsoon season on the North American continent as well. Here's the North American continent, moist air coming in. We're talking about over Arizona, and it's definitely low pressure. And when we bring that in, then we have that migration that takes place. That low pressure will migrate not east, not north, but west. But why? Why does it move west? It deals with these pressure gradients. And so what we're following here is a pressure law. Basically, high pressure will always flow to low pressure. And so when we see that and we factor in a little bit of friction, a little bit of Coriolis force, and these ideas of our temperature differences between cold air and warm air near our respective latitudes, then we're going to have a wind that is pretty much not exactly due east, but it's pretty much right across the nation. And that's what's bringing the weather across the United States at your latitude here. So we're certainly in the prevailing westerlies there. Westerlies flow in wavy paths, and those wavy features are known as Rossby waves. Usually about 4 to 6 waves that encircle a globe. So basically it's like a large carousel, and you're getting these undulations within that. And part of the job of a forecaster is watching those undulations, watching where they're at, what they're doing, how far north and south they are, how that compares to seasonal regularities or irregularities. And then that's one of the major tools that can be used, especially during winter season, because you can see so many days out in comparison to these shorter mesoscale processes that occur in the spring. They can have a large impact on weather. Jet streams are also important. So these are our streams of air we've talked about earlier. They're not very wide. They can maintain a fairly incredible speed there. But do remember, as we move up, even though we're talking about a wind speed that is multiple kilometers or hundreds of miles per hour, then we're not densely packed. Our molecules are not densely packed. So therefore, it doesn't feel like it's that fast. So it's not like tornadic vortices, not at these altitudes. We have polar and subtropical jets that we watch, and they certainly move things around. And every so often we'll have almost like a free agent as far as a pressure system. It'll break away from the jet stream and it becomes cut off. And a lot of times what we'll track is a cutoff low. And those things can be a bit pesky because they just kind of do their own thing for a little bit. And we need to get them out of the way to get this conveyor system moving things along a little bit. So here's a couple jet stream depictions here. Jet stream in the summer. Notice how the summer is up above and right at the Michigan Basin, Canadian border, dipping down there from areas in like Alberta, Canada. And that's going to set us up here for warmer weather. However, when the polar jet dips further south in latitudes, notice how it's a faster wind field. As that dips farther south, then we're not going to experience nearly as warm of a weather pattern. Because that polar jet is farther south, we're going to experience a cooling trend there. So most prevalent there is what we're following, and we do follow where that is. That's a guiding force, and it's a major frontal zone there. That's that polar front. Remember the latitude that we're talking about, that 60 degrees? You need to grab that information and kind of bring it back to this discussion. The jet stream moves faster in the winter. We have a density that's certainly at play there. During the winter, it occasionally moves north to south, and that is a big reason why, not the only, but that's a big reason why sometimes we'll have such intense Arctic cooling or Antarctic cooling. We'll get to temperatures that have wind chills that are down there at like -20. And that's where we have major disruptions. So most of the time it behaves, the polar jet behaves, and it dips down for a day or two and then it's right back up. But when it really digs in and it goes down there into our southern tier and it starts to cross Florida, then we're in for a real shock. And hopefully it won't stay there too long because our frost line, unfortunately, can be compromised, and we don't like our subterranean pipes to break. And some of our less insulated structures are certainly problematic when we have interior pipes that freeze and that water expands and creates a problem. So semi-permanent jet is a subtropical jet, west-east current, 25 north and south, so straddling the equator. It's a winter phenomenon, and that's what we're seeing here in regards to these types of cold outbreaks. So these Rossby waves, these guys here, this is the carousel that I'm talking about. This carousel circulates around, and as it does, we get these Rossby waves, kind of like a peninsula. And those Rossby waves can kind of break out. And as we have an outbreak that's cold, the forecaster can do a pretty good job of watching that. And if it gets caught in the jet stream, then we say, hey, heads up here, as that moves through this area, even though it's warm right now, in the next 10 days, 14 days, maybe even 2 weeks, we can experience a really cold spell. And those are things that we can watch. Every so often, it'll even stay intact, and that Rossby wave will get extremely elongated and dip way down here. And unfortunately, we may have a more prolonged jet, or more prolonged system of cold there. What gets really interesting is when this dome of cold air right there gets larger than normal. Then we're in for a real shock, a really challenging winter there. Ocean currents can't be left out. The Coriolis force deflects these currents, and we create gyres. And these gyres are what is indicated here. We have the North Atlantic gyre, as we have this North Atlantic stream to the Canary Current, North Equatorial Current, and that creates a large gyre. These guys are so often underappreciated. They really circulate the Earth's energy budget very well, and we don't give enough credit to these energy distributing currents. Without these guys, if we had a block where we didn't have the ability to generate the flow of energy from one part of the planet to the other, we would have a significant climate shift in so many parts of the world that probably even scientists and computer models would have a hard time understanding the outwardly reaching effects of that. Very, very challenging situation if that were to happen. The Gulf Stream is strengthened by westerly winds, and it continues northwestward when it moves into that northeastward as it moves into that area. And so that Gulf Stream is going to continue to move along that northeasterly path. And that's a pretty important current there. That's going to keep a lot of things warmer than normal, especially when we get over here to Europe. When we get onto that west coast of Europe, they're really having a beneficial heating because of that. So beachland areas there, coastal regions there are much warmer than normal. And that's thankful, and that's due to the northeast stream of the Gulf. Important ocean currents, other features here. Ocean currents do have a major effect on climate. Cold currents, we can have the dry climate affecting those. Warm offshore currents create the warm, moist climate, and upwelling here. This is where we get into a dense, rich, nutrient environment, and that begins to come up. And this leads us into our El Nino and La Nina. So when we see these types of things with our ocean currents and upwelling, what we're getting into with a normal situation is a lot of times we'll have an upwelling here around Chile, the Peruvian current and a Peruvian coastline, and we'll have upwelling somewhere in the nature of this region. And when we have La Nina, we have an enhancement where it kind of reverses that flow a little bit. But when we have El Nino, we really bring a lot of warm water into this area, and it disrupts the upflow of that nutrient-rich bottom water, meaning that the people that get the majority of their calories out of the ocean don't have their food source. And so what they've noticed is that's happened typically during their summer months. And remember, they're southern hemisphere, so southern month for them would be in the month of like December. So what they've done with the name El Nino is El Nino connects to the idea of being associated with Christmas, like the birth of the child of the newborn baby Jesus. Those types of things are connected to El Nino, and to us it seems odd because that is a winter season, but for the southern hemisphere this would be their summer season, and that's where we see that connection made with the naming. So the Southern Ocean, we have a gradual warming of the Pacific, December or January. Remember, that's summer season for them. La Nina is the opposite of that. It's colder than normal temperatures, and that brings us into this oscillation pattern. So we're going to jump into a different part of the planet here. This is a major factor in some of the forecasting, not the only factor by far, but one of another tool. When we have phases of the North Atlantic Ocean, just like we have phases of the Southern Ocean here, we can determine a little bit more about what's going to happen with the atmosphere. We're going to talk about a positive phase of the North Atlantic oscillation. When we have a positive phase, a lot of times there is a very strong correlation to above average temperatures in the eastern United States. In other words, temperatures will be warmer than normal. So when the NAO, North Atlantic oscillation, is positive, we're going to say it can be above average trending. Opposite patterns and precipitation are associated with negative phases of the NAO. So what we're looking at here is as a sample of the NAO, and whenever we go negative down here, like in this depiction with this state of undisturbed right there, when we're below that in this region, then we're negative. And if I saw that it was going negative, what I might forecast for a great portion of the East Coast, which could be on the edge of where we're located here in the Midwest, then because it's negative, then what I would state is that we would have a precipitation that would be unusual for us, and then probably a cooling trend. And that's not the only factor, but it would give me a greater long-term forecast tool as to determine, will spring get warm faster than normal? Will it get colder than normal? Will this next 10-day period get above average, below average? It's just another tool in your shed of forecasting pieces there. So on to El Nino. What's this mean for the regions? El Nino is one of these things we're still filtering through. Sometimes it can be a catastrophic impact of the economies of Chile, Peru, Australia, and other countries. Whenever you're getting your livelihood out of the water and you keep that too warm, you're going to have algal blooms that'll be intense. You can have a deoxygenation of the water. You just got too much CO2 being soaked in there to a benthic zone where you have a lot of organisms living, especially those that you're trying to get out through shallow layers. And your fisheries are just really strained there. So it can be distracting or even worse, catastrophic to these areas. We're just buffered from that because we are agricultural in the sense of land, not ocean. Arid areas can receive a lot of precipitation. We have seen that, and we can see a change in surface water temperature, certainly hurting the fish life. And we don't want it too warm. We don't want that produces almost an invasive species in the water, which is a lot of times algal blooms or red algae. And that's been that's been made fairly prominent here in the last few years. El Nino has been recognized as part of the global atmospheric circulation pattern. And when we see La Nina, it's also an important phenomenon as well. It's just not nearly as enhanced, and it kind of goes the opposite direction. So we typically don't have as strong of a correlation to weather related to La Nina, is what we think. So Western Pacific, wetter than normal conditions occur. There can be more frequent hurricanes in the Atlantic. We can see that development there. Then when we get into the Southern Oscillation, this is a seesaw pattern of the pressure between the Western and Eastern Pacific there. So that type of oscillation pattern sometimes takes place, and it helps forecasters and other persons in science get the idea of whether or not we're going to have coastal flooding. So if I'm a hydrology officer, I kind of get the idea about my inland streams, rivers, and waters. And certainly I'm going to watch that at the municipal level if I'm getting into a drought period like we have in the southern tier of the United States in the recent past. And California continues to struggle with meeting the demands of potable water for their population. Winds are the link between these changes. So when we have that link, then we see that being connected together. And here's the winds that we're looking at. This is a cross profile view, and we can see how those things connect together. These are things kind of wrapping it up for the chapter. And the overall distribution of temperature, we can have these subsidence and unstable conditions and westerlies being brought in, and it all flows together. So whenever we have the distribution of precipitation over the continents, we certainly need to expand our thought and understand that it's not just pressure over land. Our major pressures that we typically see a seasonal shift occur over the water, and that's why our oscillations over Pacific or Atlantic are so critical to our forecast. They're not the only thing, but they're definitely connected to that. So that'll do it for chapter 7. Thanks for tuning in, and not an overly technical chapter. Definitely has got some decent content. So you've got some thick material from a standpoint of new stuff. Probably you've got a lot of maps, a lot of zones, some weird words like Chinook, Kadiabatic, Mistral. Those types of things are a bit odd, but overall, as far as technicality, not too bad. So definitely a chapter you can do well with. Just roll your sleeves up, do your job as far as connecting to that vocabulary. Look at those diagrams and make sure you know those bands of latitude, 0 to 30, 30 to 60, and above 60, and then connect it to those things that we've been talking about, and we will reinforce in class. You'll have one lab in class that will reinforce this holistically, and then we will do a couple of mini labs that will reinforce the micro scale. Thanks for tuning in. See you in class.